Sir, we can start.
Hello.
Good evening, everyone. Am I audible?
Yeah, ma'am.
I hope Tausif sir is with us.
Hello. Yes, ma'am.
Okay. Good evening, sir. So moving
good
ahead with day 4, session 7, we once again have with us our expert speaker, Dr. Tausif Diwan, sir, head of CSA department, IIIT. Sir has enlightened us yesterday with his insightful session, and we are delighted to welcome him back today to continue sharing his valuable knowledge with us. So we can proceed with the session.
Thank you, ma'am.
Okay, sir.
Good evening once again, everyone. I hope the screen is visible.
Yes, sir.
So we will continue from the yesterday's lecture. Okay, so we were doing this calculations for CNN final outcome. We will take one quick exercise over here for calculation of number of parameters. Which is very important when we compare this CNN with fully connected deep neural networks. Before that, we will see the number of parameters in this particular slide. Here only one input is there, but this input is having 3 channels. First channel, second channel, and third channel. Excuse me. On this particular input, we are applying single filter, which is nothing but this filter. And we know that number of channels in the filter is equal to number of channels in the input. So we can see over here, this is nothing but the first channel of the filter. This is the second channel, third channel. When we apply one filter on the input, then we perform element-wise multiplication. Here we need to calculate the number of parameters in terms of total number of weights and total number of biases. So we can see over here, these filters are nothing but the connections, and which we call this generally as weights. So this is nothing but the first channel, and here 9 weights are associated. This is nothing but the second channel, once again 9 weights. Then this is the third channel, once again 9 weights. If we are interested in calculating the number of weights, so this will be 9 plus 9 plus 9. So likewise, it is having 27 weights. 27 connections are there. So we call this as a 27 weights. In addition to this 27 weight, we are having one bias. You can see over here, this is nothing but the single bias. How can we decide the parameters? Parameters are nothing but the total number of weights and biases. These are nothing but the number of parameters. So in this particular calculation, total number of parameters are 27 weight plus 1 bias, which is nothing but 28 parameters are there. Only single filter we are applying over here. If we compare this with that previous one, this one, here we are applying two such filters. Suppose we are interested in calculating the number of parameters in this particular slide. So we calculate number of filters corresponding to one filter, and then we will multiply it by number of filters for calculation of total number of parameters. So first of all, we will calculate the number of parameters associated with filter 1. So here we can see same 9 plus 9 plus 9, 27 weights are there plus 1 bias. One bias is associated with one filter. That's why only one bias is there. So 27 plus 1, that is nothing but 28 parameters are associated with single filter. And how many filters we are applying in this slide? We are applying two filters. That's why total number of parameters would be 28 multiplied by 2. So total number of parameters will be 56. We know that the shape of the outcome is 4 cross 4 cross 2. This 2 is coming from this number of filters that we are applying over here. If we are applying 10 such filters, then it would be 4 cross 4 cross 10. Okay. This was the formula for calculation of the output volume. Previously, we finalized this W minus F plus 1 is the final formula, but we can also apply padding, and we can also use non-unit stride. Suppose here in this animation, filter is getting shifted by one position. So stride is 1, but stride can be non-unit. It can shift by 2 position, it can shift by 3 position. So this is the generic formula, which is also taking care of some padding, which is also taking care of the stride. So see here, if P is equal to 0, means we are not applying any padding and unit stride is there, then the formula will become W minus F plus 1, which is again the same formula. And why we are taking this as twice P? Because if P is equal to 1, then padding of 1 is added, but in both the side. For example, one column is added in the left, one column is added in the right as 0 padding. So this will become twice P. So this is the generic formula. Based upon that, we will try to understand this exercise. Here we are taking one activation shape. So this is the input which is given to us, which is 32, 32, 3. This 32, 32, 3 is nothing but the input shape which is given to us. 32 is the width, 32 is the height, and this 3 is nothing but the number of channels in the input. And total in terms of activation size, how many values are there? 32 multiplied by 32, which is nothing but 1024. And 1024 is multiplied by 3. It comes out to be 3072. In this input, so far we have not applied any convolution, we have not applied any pooling. So number of parameters are 0. Fine. This is nothing but the first row. So row by row, we will try to understand this exercise. Now see the second row, which is nothing but this convolution 1. In this convolution 1, we are applying one filter. Size of this filter is 5 by 5. Stride is 1. See, padding is not mentioned over here. So definitely you may imagine that padding is equal to 0. Stride is 1. So look at this formula. Padding is equal to 0. Stride is equal to 1. Formula will become W minus F plus 1. Okay. So look at this. This is 5 cross 5 filter which we are applying. Input shape is 32, 32. So it will become 32 minus 5. Why? Because this is W minus F. Here we can see W is 32, F is 5. So 32 minus 5, it will become 27 and then plus 1. So it comes out to be 28. This is clear. On this 32, 32, when we are applying 5 cross 5 filter, then it is becoming 28, 28. From where? From which formula? 32 minus 5 plus 1. It is 28, 28. From where this 8 is coming into picture? This 8 is nothing but the number of filters that we are applying. Look at this example. This is nothing but the last figure, which is 442. What is this 2? This 2 is nothing but number of filters that we are applying. Okay. And here, this is 28, 28, 8. So this 8 is nothing but number of filters that we are applying. In terms of activation size, how many values that we are generating? It is nothing but 28 multiplied by 28 multiplied by 8. So it is 6272. Now we need to calculate the number of parameters over here. And how can we calculate the number of parameters? This 5x5 filter is applied on this input. We just need to check the filter is applied on which input. Okay. If filter is applied on 32, 32, 3, this filter convolution 1 is applied on 32, 32, 3. We need to check how many channels are there in the filter. So 3 channels are there in the filter. Then we need to finalize that 3 channels would be there with the filter also. Okay. 5x5 means how many weights are there? 25 weights. Then 25 weights corresponding to first channel, 25 weights corresponding to second channel, 25 weights corresponding to third channel. For example, if we look at this animation, this is 3x3 filter. Okay. 3x3 filter. So this is 9 weights corresponding to first channel, 9 weights corresponding to second channel, 9 weights corresponding to last channel. But here in this example, we are not applying 3x3 filter, we are applying 5x5 filter. Okay. So in this, it will be 5x5 means 25 weights corresponding to first channel, 25 weights corresponding to second channel, 25 weights corresponding to third channel. Total how many weights would be there? 25 plus 25 plus 25. It would be 75. In addition to these weights, one bias would also be associated. So total how many parameters are associated with single filter over here? 75 weights plus one bias. That is nothing but 76. 76 parameters are associated. 76 parameters are associated with single filter. And how many such filters we are applying over here? We are applying 8 such filters. Look at this. We are applying 8 such filters. So the total number of parameters will be 76 multiplied by 8. And if you perform 76 multiplied by 8, it comes out to be 608. I hope that this calculation is clear. If you are having any query or any doubt in this calculation, just look at this for 5 more minutes. We will also look at this convolution too. Then I think the things would get clear to you. Next operation is pooling. So here we are taking 2x2 max pool with a stride 2. Look at this 28, 28. On this 28, 28, we are applying 2x2 max pool with a stride 2. Then 28, 28 is getting converted into 14, 14. This is perfectly fine. In pooling operation, number of channels are not getting changed. So number of channels previously were 8. After applying pooling, number of channels would also be 8. But this is 14, 14, 8. Total how many values would be there? 14 multiplied by 14 multiplied by 8. So it is nothing but 1568. This is activation size. In pooling operation, no parameters are associated. That's why number of parameters in this pooling one is 0. Now we are applying second convolution. This time it is convolution 2. Fine. Again, same filter we are applying. Filter size is 5x5, stride is 1. But look at this. This filter is applied on which input? This is the first and foremost thing that we need to check. Filter is applied on which input? This time filter is applied on 14, 14, 4. This time filter convolution 2 is applied on 14, 14, 8. Okay. So how many channels would be there in filter? We need to check on which input it is applied. Number of channels in the filter is equal to number of channels in the input. What is the filter size? Filter size is 5x5. It is applied on 14, 14, 8. In 14, 14, 8, 8 channels are there. That's why 8 channels would be there in the filter. How many parameters are associated with one channel? 25 weights are associated with one channel. How many channels are there? 8 channels are there. So total number of parameters will be 25 multiplied by 8. 25. First 5x5 means 25 weights corresponding to first channel. Second 5x5 means second 25 weights corresponding to second channel. Third channel, fourth, fifth, likewise 8th channel are there. So total number of weights will be 25 multiplied by 8. It is nothing but 200. On top of this, we are having one bias. Okay, so total how many parameters are associated with single filter? This will be 200 weight plus one bias. 200 weights plus one bias is nothing but 201 parameters are associated with single filter. And look at this 16. What is this 16? We are applying 16 filter. So 201 parameters are associated with single filter. And how many filters we are applying? 16. So 201 is multiplied by 16. It comes out to be 3216. I hope that things are clear. Once again, we are applying second pooling. This 10 cross 10 is getting converted into 5 cross 5. 16 remains 16. Then 5 multiplied by 16 is nothing but 400. No parameters are associated. After applying first convolutional layer, second convolutional layer, we are applying fully connected layer, FC3. In this fully connected layer, it is also known as dense layer. What is the speciality of fully connected layer? In fully connected layer, each of these 120 neurons is connected to all the neurons of the previous layer. And how many neurons are there in the previous layer? These 400 values are there, 400 neurons are there. So this is fully connected layer. It means that these 120 neurons are connected to these 400 neurons in a fully connected fashion. These 120 neurons are connected to these 400 neurons in a fully connected fashion. Total, how many connections would be there? 120 multiplied by 400, it comes out to be 48,000, right? And if you consider that this 400 is input layer, this 120 is output layer. So in the output layer with each of these 120 neurons, one bias would also be associated. So in addition to 48,000 weights, how many biases would be there? 120 bias would also be there. So total number of parameters would be 400 plus multiplied by 120, 48,000 weights plus 120 bias. 48,000 plus 120, it is nothing but 48,120. After this FC3, one more fully connected layer is there in which 84 neurons are there. These 84 neurons are connected to these 120 neurons in a fully connected fashion. So total number of parameters will be 84 multiplied by 120. These many weights would be there and 84 bias. So expression will be 84 multiplied by 120 plus 84, 164. And after that, last fully connected neuron, a fully connected layer in which 10 neurons are there. As it is a classification problem, 10 categories are there. Okay, so 10 neurons are there in the output. So this 10 neurons are connected to these 84 neurons in a fully connected fashion. So it is nothing but 10 multiplied by 84 plus 10. So 840 plus 10 is nothing but 850. Yes, any doubt or any query in this calculation? If you are having any query in any of the calculation, then please feel free to ask. Fine. Now this is nothing but the generalization of convolution operation. This is W1, H1, D1 is the input which is given to us on which we are applying filters. We should know these four things, like what is the filter size, F cross F, how many filters we are applying, what is the value of stride and the amount of zero padding. Based upon the value of these four things, we generate our output volume. Output volume shape is W2, H2, D2. W2 is the width of the output, H2 is the height of the output, D2 is the depth of the output. With the same formula, we calculate W2 and H2. W2 is equal to W1 minus F plus twice P divided by S plus 1, and H2 is equal to H1 minus F plus twice P divided by S plus 1. D2 is equal to K. What is the meaning of this? D2 is equal to K. Depth of the output is nothing but the total number of filters that we are applying. How many filters we are applying? We are applying K such filters. So it is D2 is equal to K. We need to understand this second last and last point. With parameter sharing, it introduces F cross D1 weights per filter, and when we are applying k such filters, then how many weights would be there? This expression would be multiplied by k, and with one filter, one bias is associated, so total k biases. So this will become the total number of parameters, right? Yeah, this is the generalization of pooling operation, in which we take an input W1, H1, D1 is the shape of the input. It required two hyperparameters, spatial extent, which is nothing but the region of consideration, and stride. Based upon that, we generate this outcome W2, H2, D2. So W2 is defined as with the help of this formula W1 minus F divided by S plus 1. Similarly, H2 is equal to H1 minus F divided by S plus 1. D2 is equal to D1. It indicates that in pooling operation, number of channels are not getting changed. Okay, and in pooling operation, no parameters are associated. This is the second last point. And in pooling, we generally do not prefer this zero padding. It is preferably used in convolution operation only. So these are the two properties of convolution. One is parameter sharing. Second one is sparsity of connection. What do we mean by parameter sharing? Means the filter is there and that filter is revolving over the input. Okay, same parameters are there. So it is called parameter sharing. This is the summary of any CNN calculation or any formation of CNN network. First input image would be there. On this input image, we generally apply some convolutional operation. In convolution operation, we need to decide how many filters that we are applying, what is the filter size, what would be the stride, are we applying any zero padding, or all these things. All these things are decided by user. Okay, and then we need to perform several convolutional layer, extract the features with the help of feature map, and then finally these feature maps are given to some fully connected or dense layer, and finally we perform the downstream task, whether it can be classification, it can be regression, or any other task. These are some of the classic examples. CNN is the only very big networks are there. Okay, so every time it is not advisable that we train this on from scratch. Okay, and we are having some trained networks which are already trained on very huge corpus with the help of very huge compute power, etc. So we can just take that particular network and we can use it for our downstream task. For example, if we take an example, if we are interested in categorizing dog with cat, so cat and dog are nothing but two categories. It's a binary classification kind of problem. So if our model is trained that can differentiate dogs with cat, so we are having one more example or one more application. Now we want to perform categorization of dogs. For example, if we are having 3 categories of dog, now we need to figure it out which category of dog is this. Okay, this time we are not interested in differentiating dog with cats. We are interested in differentiating the categories of dog, like identifying which category of dog is this when the input image is given to us. Previously, we are having one trained model. We can take this trained model, we can just tweak some of the parameters, and it will be accustomed for our downstream task that can differentiate or that can identify the category of dogs. This process is known as fine tuning. Basically, 2 parts are there. One is pre-training and second one is fine tuning. Pre-training means this model is pre-trained on very huge corpus and it is readily available for us to use. And fine tuning means we are having very limited amount of label data. We take that particular trained model, we change some of the values of the parameters of that trained model. This process is called as fine tuning. These are all examples of pre-trained CNN model. LeNet 5, then LXNet is there. You just see here in LXNet, 60 million parameters are associated. 1 million is 10 lakh. Okay, so these many parameters are associated. This is not the detailed version of this. We will see this one. This is LXNet, in which 227, 227, 3. is nothing but the shape which is given to us, on which we are applying 11 cross 11 size filter. Stride is 4 and 96 filters we are 96 filters we are applying over here. Formula is same. 227 minus 11 divided by 4 plus 1. It is 55. So this will be 55 cross 55. And how many such filters we are applying? 96. So the shape will be 55, 55, 96. This is the shape that we are generating. After that, pooling layer is there. Then one more convolutional layer, then max pooling layer. Finally, one more convolutional layer. Then fourth convolution, fifth convolution, and after that, one more max pooling. These extracted features are given to some fully connected layers. So 2 fully connected layers are there with 4096 neuron in each of these. And after that, the last fully connected layer in which total 1000 neurons are there. Fine. This is nothing but the broader overview of AlexNet. See why we are looking at this pre-trained network, because these pre-trained networks are generally preferred in healthcare side of applications. We will see some of the usage of this. So see, AlexNet, broadly we can call that this is AlexNet, and it is having 5 convolutional layers and 3 fully connected layers are there. Input to this AlexNet is 256 colored input. See here. You can see here, this is not 256, it is 227. What we will call, we just perform this random crop of size 227 on this input 256. Total, how many parameters are associated? 60 million parameters are associated. These many neurons are there. And it took 5 to 6 days to train on 2 DGX powerful GPU. See here. As I told you that this is the pre-trained model. It is trained on very huge corpus. This was very large model. 60 million parameters are there, these many neurons. And when we trained this particular model on very huge corpus, then it took 5 to 6 days, complete days, to train that particular model on these 2 powerful GPUs. In each of these techniques, we used some of the optimization things, which is nothing but data augmentation and dropouts that we are using to train the model. We will see some of the examples of data augmentation and dropout also. This is nothing but another interesting pre-trained network, which is nothing but inception net. See, what is the speciality of this inception net? So far, we have seen all these networks in which you were either using 3x3 filter, 5x5 filter, but not a mix of all these filters. For example, look at this. Here we are applying 1x1 filter, 3x3 filter, 5x5 filter on the same input, right? A question is that why there is a necessity of applying different size filter. So the answer lies over here. You can see these 3 images are there. What is the similarity in these 3 images? All are dog images. Okay. What is the difference? Difference is that in the first image, this dog occupies almost 70% of the total image size. In the second one, it is almost occupying 40%. And in the third one, it is occupying almost 10%. Logic is that if we are interested or if we are given this mixed kind of input, okay, and we need to determine whether the input image is a dog image or not, then we cannot rely on any single size filter. For example, if this is the input, then we will prefer larger size filter, such as 7x7, 5x5. Okay, but if this is the filter, this is the image, third image, in which we may expect that we should use smaller size filter, such as 2x2, 1x1. Okay, that's why there is a necessity of to apply different size filters. The basic intuition behind inception is that we need to apply different size filter. Here, see, all are generating same width and height. It is also generating 2828. It is also generating 2828. But you can see here the depth is different. The depth of this is 64 The depth of this is 128. The depth of this is 32. From where this depth is coming into picture? This depth is nothing but the number of filters that we are applying. Finally, you concatenate all these things and you generate this shape 28, 28, 256. There are various versions of inception. For example, inception V1, V2, V3, V4. Okay. Now we will switch to that healthcare application, and then we will once again come over here and try to understand this inception V1, V2, and V3. Okay. We will explore over here two case studies. These two case studies are from my paper itself. One is based on breast cancer and another one is based on skin cancer. So this is the first case study, which is nothing but detection of breast cancer from the images which are given to us with the help of deep learning models. So this was the problem statement. Basically, breast cancer is a very lethal form of cancer. Generally, what this medical practitioners uses, they use this mammogram and histopathological biopsy images, which are recommended, and they just examine these particular things as input for recommendation of early detection of breast cancer. But here, see, there are very limited number of experts available, and this is very manual process. So the idea is that can we develop some sort of models and we can improve the accuracy and the task can be automated. Here we can see a limited accuracy is there below 80%. So here we use this data set. It is a very standard data set which is based upon the breast cancer. It is a case of binary classification. Only two classes are there, whether it is malignant or whether it is benign. Malignant means these are cancerous and benign means it is non-cancerous. Okay, these are the medical terminology. So do not get confused. We will call this as cancerous images and this is non-cancerous images. All these are in the context of breast cancer. Okay, so the first and foremost thing that you should understand from this number of images in these classes, what you can see over here. The first thing that you should note, data set is not balanced. What do we mean by this? If we are having two classes, then and number of samples in each of these classes is same. For example, 50% samples belong to benign, 50% sample belongs to malignant. Okay, then we call this kind of data set as a balanced data set. If the data set is balanced, then model training is simpler and model will perform, model will learn without any biasing, etc. But see here, this is an example of imbalanced data set where more number of cancerous cells are there and less number of non-cancerous cells are there. Okay, if this kind of imbalanced data set is given to us, then first of all we need to pre-process this kind of imbalanced data set by performing some sort of pre-processing techniques. Either you can use upsampling to that less number of sample classes, or we can use downsampling for this larger classes, or we can do some sort of augmentation techniques. For example, we can do augmentation and generate similar sort of images. Okay, this is nothing but the techniques that we should perform to match the number of samples in each of these classes. See here, these are some of the samples, A, B, C, D. Here you can see this type of samples are given to us. Based upon this sample, we need to figure it out whether it is a cancerous cell or whether it is a non-cancerous cell. Fine. Here in this break-his data set, this data set is labeled. What do we mean by this? This image is also given to us. In addition to this image, we also know that the label of this image, whether it's benign or whether it's malignant. Okay. Now, This is what we applied. This is the pipeline. We took this initial input. Now, this is our classification model that we are using. You can see these are all the pre-trained CNN model. Exception, Inception V3, ResNet XT 101, Inception ResNet V2, DenseNet 101, Exception, Inception V3. These are the two model, which is also known as ensemble in the deep learning terminology. This is Exception plus Inception ResNet V2, and this is the last one. We tested these 8 models. Okay. You just look at this before input image, between this input image and classification model, one block is there, which is called as pre-processing. In this pre-processing, we need to pre-process the images. Why there is a necessity to pre-process the image? Because see, we should provide the data to the model as what model is expecting. For example, model is expecting this size of input, then we should do some sort of pre-processing, and then only we can provide the data, or we can provide the input to the model. This is called pre-processing. We use this pre-trained model. Okay. Now we are having one limited amount of data, that is nothing but break-is. See here, this is our data. This is very limited data. You can see here over 8,000, only 8,000 images are there. But these models are trained on very huge corpus. What we will do, we will take one pre-trained model. For example, if we have taken Inception V3. Okay. Inception V3, we have taken it from scratch, which was already trained on very huge corpus. We will fine tune Inception V3 on our data. We will fine tune Inception V3 on this break-is data. Means we will change the parameters of the Inception V3 based upon this data. This process is known as fine tuning. This process is known as fine tuning. After performing this fine tuning, we expect that the model, the changed model, that is Inception V3, which we have changed just now by changing some of the values of the parameters. A feature extraction is done, and after that, we expect that the classification accuracies get increased. So after that feature extraction, once again, we are classifying whether it's benign or malignant, whether it is non-cancerous or cancerous. This is another example in which, first of all, we have taken this CNN model. For example, one video is given to us. Okay, look at this. Here, these are simply images. But imagine that in place of this cancerous images, if we are having one video of 5 seconds, okay, how can we process this particular video? Video is composed of several frames. Okay, you just imagine that a 5-second video is there. In this 5-second video, we are considering 5 frames. Okay, so this is the input. Frames at first timestamp, frames at second timestamp, frames at third timestamp. Total, how many frames are there? 5 frames are there. First of all, we apply CNN to extract the visual features from each of these. First of all, we will perform, or we will apply CNN to extract the visual features from each of these frames. After extracting these features from each of these frames, this is the sequential input. Ultimate meaning is that some timestamp or temporal ordering is involved over here. What do we mean by this? Timestamp, input image, frame at timestamp 0, frame at timestamp 1, frame at timestamp 2. So this is called temporal ordering involved over here in the input. And for processing this temporal ordering, we are having sequential model. Generally, we use RNN, LSTM, GRU, bidirectional LSTM. So here we can see with CNN, we are extracting the visual modality. For temporal ordering, we are applying LSTM, and then we are applying final dense layer. And then we are generating this outcome over here. This type of model is nothing but ensemble model, where we are applying CNN as well as LSTM. CNN is responsible for extracting the visual information, and BiLSTM or LSTM, which we are using, is used for extracting the sequential or temporal features information. This is what we proposed when we perform the ensembling. For example, look at this. This is something Look at this sixth one, where we are calling this exception plus inception V3. Okay. So, for example, this is my input. First of all, this input is given to exception, and the same input is given to inception V3. Fine. So what is happening over here? Feature extraction is performed by inception V3 also. Feature extraction is performed by exception. After feature extraction, using each of these models, we extract the features and then we give it to LSTM. See, 5 frames are there over here, which is once again given to sequence model. Then here, 5 frames were there. Features are extracted using inception V3. Then for temporal or sequential modeling, it is given to LSTM. After that, some pooling layer, dropout layers are there. You do not go in the detail of this, but what is happening? Feature extracted from this first pipeline and features extracted from this second pipeline. These both extracted features are concatenated. See, it is not addition. This is concatenation. Features extracted using inception V3, features extracted using exception. These are concatenated, and after concatenation, we give it to some fully connected layer. Then we apply some sigmoid function, and then we calculate this binary cross entropy loss. And then finally, this outcome is calculated. This is what we proposed in that paper. We call this as ensemble deep model for breast cancer classification. This was all these things in the context of parameter calculation. Do not go in the detail of this, but at this moment you can just learn this. For example, this is the input 299, 299, 3. Okay, and this is the output of this 299, 299, 3. On this we are applying this model. This is the first pipeline. This is the second pipeline. After that we are adding both of these, and finally classification layer. This is the performance matrix. We will also look at the things on this performance matrix. Generally in classification, we focus on improvement of accuracy, precision, recall, F1 score. We will go through these particular things a little later. So these are the results that we obtained. When we applied exception plus inception V3, this is the ensemble model. Accuracy we achieved 97.5%, and these are the weighted average. Precision, recall, F1 score. So you can see this is the result obtained. Then for some other combinations such as exception plus inception resonate V2, we achieved this much accuracy, and these are the weighted average for precision, recall, F1 score used for this ensemble. And then last one, inception V3 plus this inception resonate V2. Okay, so here we achieved this much accuracy. So you can see here exception plus inception V3 is performing tremendously good. Now, yeah. Okay, so here this paper was published in this Multimedia Tools and Applications journal. The title was this BRC breast cancer detection using multi-channel deep learning model. So here you can see this is nothing but multi-channel deep learning model. This is the first channel in which we are applying first pre-trained model. This is the second channel in which we are applying second pre-trained model, and features are extracted from with the help of both of this pre-trained model. Extracted features are concatenated, and then it is given to final classification layer. Okay, now we come over here, and then we can see exception plus inception V3 is performing good. Okay, but thing is that we cannot simply say that this model is performing good and this is our results. See, with each and every result, there should be some justification or there should be some logic behind this. Like, what question is there? Like, why we are getting improved result with the help of this ensemble exception plus inception V3? Why we are getting improvised result with this? So you need to relate this. You need to relate this with this architecture of exception and inception V3. See how you will get the answer of this. Why exception plus inception V3 is performing good? You should see the architectural level of exception and architectural aspects of inception V3. Okay, now you need to relate this achieved outcome in terms of accuracy, in terms of precision, recall, F1 score with the architecture of exception and inception v3. Fine. Look at this. Now you can go to the inception network, which we are learning on this stage. This was my inception network, the basic inception network. In inception network, various optimizations are proposed in terms of successor. For example, initially inception v1 was there. This inception v1 was trained on very huge corpus, in which total 1000 classes are there. That is nothing but ImageNet dataset. And okay, so this is the deep learning model that we used, and all these things are there. It was the logic behind inception. We need to use different size filters. If we use same size filter, then it is not very much useful when the object in the image is having smaller size, or when the object in the image is having larger size. That's why we go for a different size filter, and then we can just concatenate the extracted features. This is inception v2. In inception v2, we are just handling this representational bottleneck. For example, we are using some sort of smart factorization techniques. Look at this. Here you can see this 5x5 convolution is there. 5x5 convolution means how many parameters? Just look at that. 5x5 means 25 parameters are there. We break this 5x5 convolution to 2 3x3. Look at this. This is first 3x3 and this is second 3x3. This is called factorization of the convolution operation. Okay, and what we are doing? We are handling representational bottleneck problem. For example, this model will become the lightweight. What do we mean by lightweight? Lightweight means less number of parameters would be associated over here. 5x5 means how many weights would be there? 25 weights will be associated. But if we are using 2 3x3 instead of 1 5x5, so total how many weights would be there? First 3x3 means 9 weights. Second 3x3 means once again 9 weights. 9 plus 9 is 18 weights are associated. But when we are using single 5x5 filter, then how many weights? 25 weights. You can see 33%, almost 33% reductions is there. What we can do? We can replace, listen carefully, we can replace one larger filter with multiple smaller size filter. I am repeating this sentence. We can replace one larger sized filter with multiple smaller sized filter. Okay. So with this we can reduce the number of parameters. With this the model will become lighter. This was inception v2. Fine. After that, some more modifications are proposed in inception v2, and some more modifications are proposed in inception v2, and then inception v3 is proposed. Why we are learning inception v3? Because inception v3 we used in that breast cancer detection problem. These are the 4 optimizations or measures that were applied in optimizer side. See, this is the gradient descent or backpropagation techniques is there, in which we need to optimize this gradient descent. There are various standard gradient descent optimizers are there. For example, RMS prop, momentum, the combination of RMS prop and momentum is called as Adams optimizer. Then factorized convolution we can use. Then batch normalization is proposed for reducing the regularization, etc. And label smoothing. These are the 4 things which are proposed. And then inception v3 came into picture. Now we have understood the speciality of inception v3. We have understood the speciality of inception v3. Okay. Now we need to correlate these speciality or these features of inception v3 with that improvised result. Which improvised result? This one. This one. This is the result we are getting with this combination inception v3. Now we need to relate the architectural advancement of inception v3, which is this one. Which is this one. Okay. And we need to relate this with that improvised result. Like what would be the speciality of Inception V3. Due to that, we are getting improvement in the results of that breast cancer classification and how it is related to the optimization or improvement in the performance metrics. This is nothing but the justification of the result. Every time in all the research paper, you can see result and justification. Result means just presenting what you are observing as a result, and justification means the logic behind it. Okay, so this is nothing but the justification. One more thing that I should emphasize over here. Yeah, this was once again the similar problem. Once again on breast cancer detection, we applied some different techniques over here, which is nothing but generative adversarial network. And this deep convolutional network that we presented for breast cancer prediction, here we applied this image data. In addition to this image data, we applied augmentation using some DC GAN. GAN is nothing but generative adversarial networks, and then feature extraction using BGG16 followed by features extracted, then proposed neural network and interpretability. All these things are explored. Ultimately, what we are applying, this was the image data which is given to us. On that image data, we are applying augmentation. Augmentation is a very generic techniques. With the help of augmentation, we can apply or we can generate similar types of images. We will explore some of the things of augmentations and then we will come back over here. Now see, we will see the augmentation things over here. See, this is the data augmentation. Images are there. We need to do some changes in the images and we need to come up with the similar sort of images. There are various techniques for augmentation. For example, we can apply flipping. So this, you can see, this is nothing but my original image. On this original image, we can apply horizontal flip, we can apply vertical flip and generate similar sort of images. Okay. For example, if it is handwritten digit 0, then on this handwritten digit 0, you just apply vertical flip and generate similar images. Okay. That once again, the label would be same. That will be handwritten digit 0 only. Fine. So this type of operations that you can perform, it is known as augmentation. There are various techniques of augmentation. This is once again another technique for augmentation, which is called as rotation. So this is the original image. You can see here 0 degree. This is the original image. You can rotate this image by 10 degree, 20 degree, 30 degree and generate similar sort of images. Okay. This operation is known as rotation. Then zooming you can perform. This is the original image. You can zoom it by 10%, 20%, 30% and generate different images. Then width and height shift you can do. In center you can see original image. When we see this width shift, then you can generate this left and right images. When we can apply height shift, then you can generate up and down sort of images. This is homography. Then changing the brightness, like just channels are there, you just change some of the parameters of those channel values, then brightness of that particular image is converted. You can also do channel shifting, and all these are nothing but the augmentation technique that you can perform. All these are nothing but the plain augmentation technique. What we applied over here in this particular paper, we applied this one. We apply augmentation using DC GAN. Okay. GAN is nothing but generative adversarial network. It is once again another neural networks. And with the help of DC GAN, it is improvised sort of augmentation that we applied. Improvised sort of augmentation that we applied. And after applying this improvised augmentation, when we extracted the features, then it is given to the classification model. And finally, we will get the improvised result. See, ultimately, this is a game of feature extraction and feature representation. Ultimately, any classification or any prediction problem is a game of feature extraction or feature representation. Okay, the effective features you extract, it is very easy to extract, or it is very easy to get the improvised performance metrics. Okay, now see what we did after this. You can see for when we train for 60 iterations, then these are the results. When we train for another 20 iterations, then we get this results, and lastly this results we got. This was the second case study. Okay, this was in the context of what? Breast cancer. Second case study is once again from my paper only, which is nothing but skin cancer detection. This time we have taken data set of skin cancer. Okay, and what we perform, we propose this model. This is my input. It is 224. On this input, we applied two things: machine learning techniques also and deep learning techniques also. You can see there are three things over here. This one, first, second, and this block, which comes under this machine learning, and then second block, pre-processing augmentation and modified VGG19, this comes under deep learning. We applied machine learning as well as deep learning. Okay, before applying machine learning models such as logistic regression and linear support vector machine, we applied some pre-processing techniques in terms of contourlet transform and local binary pattern histogram, and after that these features are concatenated. Now we are having a list of features. For example, 100 features are there. For this 100 features, not all the features are very much important. For this, we need to extract the important features, for which there are various standard algorithms such as principal component analysis, linear discriminant analysis, multiple discriminant analysis. All these algorithms are there. We can apply all these algorithms and we can extract the important or dominating features. After applying this principal component analysis, we extracted the dominating features or the important features. These important features are given to logistic regression model, as well as these important features are given to linear support vector machine. Now, what is happening in deep learning side? This is my input. First of all, we are performing pre-processing and the normal augmentation. After applying pre-processing and augmentation, this is given to modified VGG19. VGG19 is once again a pre-trained CNN model. Okay, it is given to this. What do we mean by modified VGG19? Modified VGG19 means VGG19 was the pre-trained model. We fine-tune this VGG19 and then we call this as a modified VGG19. So now we are having three models to which we are giving the features. We are having three models to which we are giving the features. First one is logistic regression, second one is linear SVM, and third one is modified VGG19. All these are performing skin cancer classification. Finally, we are just giving one weighted ensemble over here, voting classifier. For example, what is the result of this? Whether it is cancerous. What is the result of linear SVM? Once again, it is giving cancerous. What is the result of modified VGG19? It is non-cancerous. So we apply one sort of voting classifier. We go with the majority and then we just finally do the classifications. This is what we proposed in this paper. This was the paper, skin cancer detection using ensemble of machine learning and deep learning. So here we can see these are the previously published research papers. In comparison to this previously published research papers, this is what we observed. 93% accuracy, 92% precision, 92% recall, and then F1 score is 93% by applying this particular model. See, this was what? This was the binary classification. What is the meaning of this binary classification? We just need to identify whether the image is cancerous or non-cancerous. Okay. Now we extended this for multi-class skin cancer classification using deep model. For example, this was the problem statement. Skin cancer accounts for 1/3 of all the diagnosed cancer worldwide. The dermatologists have an average accuracy of 62% to 80% in skin cancer diagnosis. Ultimately, in cancer detection, it can be any cancer: skin cancer, breast cancer, lung cancer, any tumor detection, etc. It is a game of early detection. It's a game of early detection. Early detection of cancer can lead to prevention and can lead to proper diagnosis and the treatment. If we are detecting the cancer in third or fourth stage, then it will be of no use. So with the help of this deep learning or machine learning model, we are interested in early detection of the cancer. Okay. So for early detection, the average accuracy of dermatologist is 62 to 80% for skin cancer diagnostic. This is the data set that we have operated upon. Here, this is the standard data set. Name of this data set is M10,000 data set. Total, how many images are there in this data set? 10,000 images. All are cancerous images. All are cancerous images. Fine. Here, aim is not that we need to find whether the image is cancerous or non-cancerous. Here, we need to find which type of cancerous image is this. So this is the first type, melanocytic. Second one, melanoma. So melanocytic is nothing but this particular first category in which total 6,700 images are there. Melanoma is another category which is nothing but these many images are there. Then benign, then basal cell carcinoma, then this one, vascular, and last one. So these many images are there. If you count this total number of images, it comes out to be 10,015 images are there. Now we are interested in training the model. Once we train the model, then we will evaluate on the testing data. Okay. This is some of the sample images. See here, this is nothing but, see here, this is melanoma. Okay. This is one example of each of these. This is what we proposed. Input image is there. On this input image, we are applying this pre-processing, and then we are generating this size. After generating this size, we are giving it to the pre-trained model. It can be Inception V3, it can be ResNet 101, it can be Inception, ResNet V2, Exception. Then after applying any pre-trained model, we need to fine-tune that pre-trained model. Okay, that is nothing but fine-tuning. After performing this fine-tuning, we are extracting the features which are given to these particular cell. Okay, and then finally we are just determining which category of cancer is this. That is an example of multi-class classification. This is what the table proposed, like the results with the comparison. These are some of the previously published articles, and this is the bold one, which is nothing but our results. Here we can see some improvement in the results are there in terms of accuracy, precision, as well as recall. Yeah, this is what we published, skin cancer classification using deep CNN. Now, I would like to explore some of the things on this accuracy, precision, recall. Just give me some time. Yeah, so this was, we were looking Inception V3. We will quickly sum some of the things. For example, this is Inception V4. In this Inception V4, we are just doing some sort of uniformity. We are applying reduction block. This is an improvement in Inception V3. Then we are applying 1x1 convolution. We have seen that 3x3 filter we are applying, 5x5 filter we are applying. In addition to this, we can also apply 1x1 filter. Okay, 1x1 filter is nothing but single value is there, which is 1x1 filter. 1x1 filter is just like pooling operation, but there is some difference between 1x1 convolution and channel-wise pooling. In 1x1 convolution, it can be considered as channel-wise pooling. In pooling operation, we just reduce. In pooling operation, we just reduce the width and height. But in 1x1 convolution, the depth is getting reduced. Okay, this is the main difference. Yeah, these are some of the tips for starting CNN problems. We can use open source repository. We can use some transfer learning to fine tune our data set. We can use some data augmentation techniques, etc. For example, this is the example of transfer learning in which we are provided with network A. So you can see that this is nothing but our pre-trained model, network A. On this pre-trained model, we are just performing this transfer learning. So this part is same, okay, and this is nothing but the extended part, which we can fine tune this. Okay, this is called as fine tuning. This is one application which is nothing but the localization problem. Here we can see image is given to us and we need to localize the object in that image. For example, this is the car object in this image. We need to localize, and what do we mean by localization? We need to do one bounding box that can cover that particular image in terms of height, in terms of width, in terms of center, okay, etc. And which object is this? So total 5 things are there: width and height of that bounding box, and center of that bounding box, and which category is this. For example, if we look at this particular image in which 3 objects are there, so 3 bounding boxes would be there. This is dog, then second one is this bicycle, and then third one is this car. This is again interesting problem of CNN, which is called as landmark detection. In landmark detection, some points are determined. Based upon those points, we just need to locate the landmark on the face of the input person. And after locating this landmark, based upon the value of this landmark, we can identify that particular person, like which person is this. Okay, so this kind of problem is known as landmark detection. Another interesting problem is known as neural style transfer. Look at this. Neural style transfer refers to a class of software algorithm that manipulate the digital image or video to adapt the appearance or visual style of another image. For example, look at this first image. This is the first image. Fine. On this image, we are applying this second one, which is nothing but called as style. First one is image, second one is style. We are applying this style on this input, and then we are generating this image. This process is known as neural style transfer. This is object detection problem. We just need to locate that particular object which is moving. Okay, so all these problems are very important when we perform some object detection or activity detection problem, or in automated driving car, etc. Okay. Lastly, I would like to explain some of the important performance metrics that we have used over here, such as accuracy, precision, recall, etc. Okay, these are the performance metrics of classification. I will just try to wind it up very quickly. Accuracy, recall is also known as sensitivity. Then precision, specificity are there, F1 score, etc. Look at this. All these things we will try to understand in the context of binary classification. For example, on horizontally, we are just writing this model prediction, and vertically we are writing the actual model labeling. Okay, and here we are interested in learning all these things in the context of binary classification. Only 2 classes are there: category A or category B, or very specifically, we call this as positive or negative classes. So in actual, this is nothing but the positive and this is negative. Fine. Actual means the actual label of this particular sample. And this is the model prediction, like what model is predicting, whether model is predicting positive or whether model is predicting negative. Based upon this, we are having true positive, false negative, and true negative. Okay. So here we will first try to explain true positive. In this true positive, false negative, true positive, second one is nothing but model prediction. And the first word is nothing but whether it is true or false. For example, if we call this as true positive, in true positive, what is positive? Positive means model prediction. Fine. Model prediction is positive and true indicate that it is true. Actual label is true. Model is also saying that it is positive. So we are calling this as true positive. Come to this true negative. In this true negative, model is predicting that it is a negative and this is true. Actual label is also negative. This is true. Fine. Now, false positive. False positive means model prediction is positive. False positive means model prediction is positive and this is false. This is false. Actually, this should have been predicted as negative, but it is wrongly predicted as positive. That's why we are calling this as false positive. False positive, actual label is negative. Okay. False negative, model prediction is negative. It is false. Actual label is positive. Based upon this, we will try to define accuracy. Accuracy is nothing but the correct prediction divided by the total number of samples. Correct prediction means predictions which are correct. Which predictions are correct? This true one. These predictions are correct. So in numerator, it is true positive plus true negative divided by total number of examples. Now, just imagine that balanced class is there. If it is a balanced class, okay. If it is a balanced class, like 50% positive samples are there and 50% negative samples are there. And suppose you just take one random model, and now you are interested in evaluating that model on this particular data. So this model is predicting all the samples as positive. Okay. What is the accuracy? Accuracy would be 50%. Accuracy would be 50%. It is not performing good. It is true in the context of balanced data set. Just imagine that data set is not balanced. In that data set, 90% of the samples are positive and 10% of the samples are negative. 90% positive and 10% negative. Once again, you have taken one random model. Okay, this model is very random. We also don't know what the model is doing. Okay, and this model is predicting all the samples as positive. Now, look at this imbalanced data set in which 90 positive samples are there and 10 negative samples are there. And this model is predicting all the samples as positive. Okay. Just because of that, the data is imbalanced and it is predicting all the sample as positive. It is some random model. We don't know what the model is doing. And the model accuracy is 90%. Look at this. What is the value of true positive here? True positive will be 90. True negative will be 0 because it is not predicting anything as negative. That will be 0. So accuracy will become 90%. Okay. Now, based upon this 90% accuracy, can we conclude that model is performing very good? No, because this is one random model. We cannot conclude that. That's why there is a necessity of other performance metrics such as recall, precision. Okay, recall is taking care of false negatives. For example, look at this. This is the formula for recall. True positive divided by true positive plus false negative. Here we are interested in minimizing this false negative. Ideally, false negative should be 0. Why we are interested in removing or why we are interested in mitigating the false negative? Just look at that. Look at one scenario where we are interested in predicting cancer in early stage. We are interested in predicting cancer in early stage. Okay. What is false negative? False negative means what? Patient is cancerous. Listen carefully. What is false negative? False negative means patient is cancerous. Model is predicting that it is negative. Model is saying that it is non-cancerous and it is false. See what will happen after this. Actually, the patient was cancerous. Just because of that, my model is saying that it is non-cancerous. I am not giving treatment to the patient. Now the patient which was previously on stage 1, he is entering into stage 2. He is entering into stage 3. Just because of that, my model predicted wrongly and I started treatment little later. This is the problem. In such type of scenario, we are explicitly want that false negative should be 0. Ideally, false negative should be 0. What would be false positive here? What would be the false positive in the context of cancer detection? What is false positive? False positive means patient was non-cancerous. Model is saying that he is cancerous. Model is predicting that he is cancerous. You just started the treatment. Fine. You started treatment, and after some time you come to know that the patient is non-cancerous. You stop the treatment. See, it will not cause any problem. It completely depends on application to application, which application you are targeting. For example, we will take one more example, that is precision. Precision, the formula is true positive divided by true positive plus false positive. In some of the application, we are interested in minimizing false positive. In some of the application, we may be interested in minimizing false negative. Just like in cancer detection, we were interested in minimizing false negative. But if we take an example of email spam, we are interested in minimizing false positive. What is false positive? In the context of email spam, it is a spam or it's a non-spam kind of email is there. What is false positive? False positive means mail is coming to my mailbox and my model is saying that it is spam. It is spam. And just because that my model is predicting that it is spam, it is going to spam folder. Actually, that was not a spam. That was an important mail. And just because that my model is predicting that it's a spam, it is going to spam folder, and I am missing that important mail. This is problematic. On the other hand, if we can say that what is false negative? What is false negative in the context of email spam? False negative means model is saying model is saying that this is not a spam email. This is not a spam email. If it is not a spam email, this is coming to my inbox. After opening that mail, I come to know that this is spam and I am just deleting that mail. It will not cause any problem. But look at the other side of the coin. False positive is dangerous in the context of email spam. Similarly, false negative is dangerous in the context of cancer detection. In some of the applications, we may be interested in both precision as well as recall. We can take harmonic mean of precision and recall, and that we can define as F1 score. So this is all about that performance matrix. Yes. So I think we can stop over here. Probably after that, next session would be there. Yeah. If any questions are there, then we can take some of the questions, and then we will stop. Thank you.
Sir, in one of your slides, you were discussing about modified VGG 16.
Just a minute. Yes, please.
Sir, in one of your slides, you were discussing about modified VGG 16.
Right.
Sir, what type of modification in the pre-trained model you did, sir?
Modification in the context of updating the parameters of that particular. It is nothing but fine tuning.
Okay, thank you, sir.
At architectural level, we are not doing any changes in that.
Okay, sir. Thank you, sir.
However, if we are really interested in doing some sort of modifications, so it depends on application. For example, in the original VGG 16 or original VGG 19, if 2 neurons are there in the last layer, but we are interested in solving some other problem in which 3 categories are there, so we need to add 1 more neuron in the last layer. Okay, this can be considered as one of the modifications in the architectural level.
Sir, one thing is noted that there are too many parameters in fully connected layers or dense layer.
Right.
Sir, can we anyhow not use this dense layer to classify either it is binary class or it is multi-class?
Actually, this dense layer or fully connected layer are preferably used for summing up all the expected features from the previous earlier layers. For example, if many convolutional layers are there or multiple pipelines are there, from each of these pipeline we are extracting the features, and lastly we need to club all these extracted features. For this we can use this fully connected kind of layers.
Thank you, sir. Thank you. It's been always a pleasure to listen you, sir.
No, sir,
Your
thank you, sir.
insights,
Thank
your
you for
knowledge,
inviting.
your insights, your knowledge, your perception to look at the problem and provide the solution is tremendously, sir. Thank you so much.
Thank you, sir.
Over to you, Sadia ma'am.
Thank you, sir. Thank you, Dr. Tausif. It was truly an amazing session full of fundamentals of deep learning, as well as looking for two different methods. Let's proceed for the next session. Okay, we will take a 5 minute of break, then we will proceed for the next session.